So let me thank Ankur, Vinay, and a whole bunch of you in between who've been organizing the in-house symposium this year. Also, it allows people like me to sort of, because we are amongst, friends and family, to talk about things that I've just started to think about. And essentially what I'm going to talk about is a phase diagram for Dynamo action, thanks to Tushar and Pallavi's work. At least, Vinay, many of you actually work on this, unlike me, so you have some basic idea. But I'll tell you a little bit about what we've been sort of trying to do in this business. So essentially, as you've heard for at least 3 talks, large magnetic fields are ubiquitous, right? So there could be, in these very nice liquid sodium experiments, all the way to star formation, interstellar medium. I hope I got the length scales right in this sort of arrangement. And the question that, worries a lot of people is that how do large sustained magnetic fields arise in these conducting fluids? I'm not going to answer that question really. And that's essentially what the dynamo problem is. And typically, as Tushar does, you look for answers within the framework of what's known as MAG turbulence. So that is, you take the U field and the magnetic B field, you write down the sort of Navier-Stokes-like looking equations, but these are coupled equations in interesting ways. And the dynamo problem for an outsider, for a novice like me, essentially is very trivially, I should state it, as that if I take these equations and if I start with a very tiny seed magnetic field, does that magnetic field grow in time? All right? And what we know, I think we know much, much more than this. So let's say it. What I know essentially is that, in 3 dimensions, dynamo action is possible. In 2 dimensions, there are no dynamos. There's famous anti-dynamo theorems, etc. What I have not said, but we can discuss over lunch, the reason why I got interested into this business is because there are some very nice recent results, starting with the work of Kazantsev, which is not so recent, but people have played with this model, which sort of connects the idea of dynamo action to flow regularity and, what it means for an optimal regularity of a flow to sustain dynamos. But, before we get there, so the question that I'll try to answer here is that are there an upper and lower dimensions? The word critical is just to be fancy here, but are there upper and lower dimensions within which you can have dynamo? As I said, at d equal to 2, there are no dynamos. At d equal to 3, there are dynamos, but could there be a range of dimensions which permit dynamo? And on either side of these dimensions, you don't get dynamos. So this question essentially was asked and answered by Sugan in his thesis, and we've sort of been indebted to my good friend Giorgio and Dario, who've also helped us along. Now, to answer that question, there's a problem. And the problem is that it's kind of impossible to probe this question with those MHD equations, even numerically, in arbitrary dimensions D. Especially as Tushar pointed out, you can never reach things, frontal numbers, etc., which are realistic. So we look for answers in other theoretical approaches. This is not to scare you, but just people in the audience who do turbulence, it's not all about numerical simulations. So in hydrodynamic turbulence and Navier-Stokes, for example, when people start to look for such questions, they try to adapt various sort of theoretical models with different degrees of cheating. And what we'll try to do is try to construct, using the spirit of what's known as EDQNM, I'll just tell you what that is in a minute. What we, or rather Sugan, really constructed was a closure model, which we are calling the MHD EDQNM model, to study the dynamo problem in arbitrary dimensions D. And now I will show you the model. I won't go through the derivation, when you'll see why. So what happens is you begin with the good old MHD equations, which Tushar showed, and then you do certain levels of approximations. You define these correlators, and then you write down essentially an evolution equation of what people in the business would call the spectra for the U and B fields. These sort of evolution equations have all these horrible looking transfer terms, which are given by these d-dimensional integrals. Essentially, what this is telling you is how energy is exchanged between the magnetic and the fluid field. All right, so those of you who are interested in the derivation, we can do this after the talk. And just as a consistency check, we sort of made sure that when the magnetic field is set to 0, this obeys really d-dimensional fluid turbulence, something which was introduced many years ago by Fournier and Frisch, and others have worked on it in the past. And when you do have a magnetic field, the only sort of self-consistency check that we have is the dynamo problem in 2 and 3 dimensions, or the MHD problem in 2 and 3 dimensions. And we can check from this sort of horrible set of equations with all these d-dimensional factors, we can check that certainly at 2 and 3 dimensions, our model reduces to what it should. And this is just a schematic for any of you who are doing closures, just to show where these integrals exist in the wave number space. All right, so now quickly the results. So what are we after? What we are after is we want to understand if the magnetic energy, starting with a very tiny magnetic energy, grows in time. So because the initial energy is very small, you can linearize those equations, and effectively you can write down the evolution equation of the total magnetic energy, which follows this, which also has a sort of complicated form, which comes from the closure equations. So the heuristic picture, and this is really naive, it's not as detailed as what Tushar was saying, is the following: that you can have dynamos when you have a dominant transfer coming from U to B, and you cannot have dynamos when the dominant transfer at large scales goes either from B to U, or even if you have a U to B transfer, that's quickly being damped out because that's happening at small scales. So let's see what happens to our closure models. So this, for example, is a plot of the total magnetic energy as a function of time, and the different curves are for different dimensions. So you can, if you can't read the legend, just trust me on this, you immediately see that at d equal to 2, after an initial rise in the magnetic energy, it quickly goes away, as it should be for the anti-dynamo theory. For d equal to 3 and a whole bunch of dimensions in between, the magnetic energy rises and eventually saturates. For some of these curves, I haven't quite shown the saturation, but they do saturate. And then at large dimensions, again, you have the same feature that you see at d equal to 2, grows and comes down. So a good indication that there might be an upper critical dimension beyond which dynamo action doesn't happen. So there are there are ways to analyze these equations and see why you have this behavior. So I'll just flash the results and we can discuss the mathematics of this. So here, for example, now this looks a much more complicated diagram than I thought it would when I first made the slide. But for example, if you're at d equal to 2, where you do not have dynamos, these are all the different transfer terms plotted against each other. All that you need to worry about is this black curve, which gives the net integrand in the equation that I showed you. And there you see, as a function of k, eventually this guy goes negative, which means that the magnetic energy is sucked out of the system, and hence no dynamo. For dimensions between these critical dimensions, so this is an example from d equal to 4. Again, just look at the black curve. You see, as a function of k, this is a, it's a cumulative integral, really. You see that eventually it saturates to a positive value as large k, so it's an integral. The integrand integrated from 0 to k plotted against k. All right, so what would be known as a cumulative distribution, which shows that the net transfer is always happening from U to B, which leads to the dynamo action. Again, when you go to much higher dimensions, dimension 8 in this case, you end up again with a drop in this curve, which again gives you the no dynamo picture. So the take-home message is the following. Excuse me. This is a phase diagram in dimensions and time. You can look at the largest time. This is just to show how it grows. So between these two dashed lines, you see that magnetic energy at large enough times saturate to a value which is roughly of the order of the fluid kinetic energy. On either side of these dashed lines, you have, even if you have an initial growth, eventually the magnetic energy dies, which shows that there is no dynamo for dimensions on either side of these dashed lines. What we estimate really is that the lower dimension is 2.04, not 2, so you can have a no dynamo just a little beyond 2. and the upper dimension is 6.5. These numbers are interesting for those of you who've sort of done some level of fluid turbulence, maybe no one in this room, because they sort of market, they demarcate certain things about fluid flows, their regularity and their chaoticity. All right, so this is our sort of central message, take-home message that I wanted to convey. But apart from that, and I really think this is a very interesting result that Sugan came up with, is the fact that he was able to develop a d-dimensional closure model for MAG turbulence, something that we know how to do in fluid turbulence, but much harder to do in these couple set of equations. And future work is to incorporate the effects of compressibility. We know how it can be done in our closure models, but it has to be done. And so at some point, hopefully this will be done, and we live to tell the tale of that. Okay, so I'm done, and I have 1 minute left, so well in time. Thank you.
Mr. Samriddhi, so questions?
Yeah, Irshad. Yeah. Sorry.
Maybe I can ask till then.
Well,
Good.
Is there so in D equal 2, you're saying there are some theorems which just prohibit dynamos from existing?
The expert is sitting next to you.
My question is not that, actually. So is there something similar for higher D? This 6.5
This 2.0
higher than 6, 7,
well,
I don't know.
Yeah, okay. So the higher dimension, the way the things are prohibited, at least within the closure, it's a very different mechanism. In lower dimensions, in the no dynamo phase diagram, we see there's never a net exchange of energy from the fluid to the magnetic field. Beyond the upper, so again, especially those of you from the statistical physics community, I'm using this word as a surrogate. So beyond the upper critical dimension, what we have is at large scales, there is a small transfer of B to U. At small scales, the fluid does pump in some energy into the magnetic field, but the magnetic dissipation that Tushar was talking about kills it off. So again, you end up with a no dynamo scenario. So the way you have no dynamos on either side of this is slightly different. The net effect is the same.
Yeah, in fact, in the plot that you showed earlier, in which you have plotted for different dimensions.
The transfer terms, yeah?
Yeah. No, the R of T.
Okay, yeah.
Yeah. So is it true that higher dimensions decay even faster?
Yeah.
Like
So the higher dimensions drop down even quickly. That's because of the small scale effect that I was telling you about. Yeah.
all right.
Yeah, hi.
Yeah, sure.
So in this plot itself, as you increase the dimensions, the saturation time is also sort of increasing, right? So do we know why?
No.
Something like that.
I mean, we may know why, but I don't know why. So, I mean, there was no way to estimate this time scale from the model that we have.
Okay, and regarding this range of dimensions, generally from the anti-dynamo theorems, I know in 2 dimensions, the equations will decouple and separately they will become some diffusion equation. So at this particular upper dimension, is it same thing is what happening, and it's not clear because I expected as the dimension increases, everything will complicated, more coupling will happen and so on. So
no, what happens is, again, keep in mind this is a closure model. So essentially, you take your MHG equations, you hit them with powers with a factor of B, and you get a hierarchy, and then you close the cubilance, right? I mean, that's the rough derivation. So when you do that in arbitrary dimensions D, you essentially need to integrate various D-dimensional triads. So these are something like a Feynman diagram, which you need to integrate out. So what happens is when you are working with those triads in higher dimensions, and again, we do not have a complete theory of this. I mean, we know the algebra, but not why the algebra is what it is. What you end up having is that there is a differential rate of transfer. So at large scales, you get U to B to U. At small scales, you get U to B. But at small scales, also the damping is effective in the MAG, and so it washes out. So what we do know is that you will have these upper and lower dimensions, but the values may change as you change the magnetic Reynolds number, the Prandtl number, or the compressibility of the flow. Right? But the fact they exist, I think, is kind of I'm happy to conjecture that they exist from theory.
And just regarding the last point you mentioned, these two numbers, 2 and near 6.
Yeah.
So how this is really important in the fluid dynamics, it's not clear to me.
So this goes back to some old field theory work by Frisch-Fournier and others, and later some of us also worked on this, was the fact that, in 2D, there is what's known as an inverse cascade of energy because of two invariants. So it turns out that this conservation law actually is not only exact at d equal to 2, but it survives till d equal to 2.03. We got 0.4, but okay, let's not quibble about, 2.07. I don't remember the exact dimension, but just epsilon above d equal to 2. So what my gut feeling is, I shouldn't blame my collaborators, is that this persistence in the fluid case of an inverse cascade, which means that your small k modes are getting energetic, also leads to the non-dynamo existence to 2 plus epsilon. At large dimensions, there are very nice, again, field theoretical results in arbitrary dimensions, which shows that the nature of chaos, Abhishek gave a talk yesterday on this, but the chaotic nature of fluid turbulence undergoes a certain transition. It becomes much more mild at dimension 5.8 something. Again, I don't remember the number offhand. So what we are trying to understand is whether this, again, 6.4, because as you know, these are field lines being stretched, right? For Dynamo, the simplest pictures, you have field lines which are being stretched. So if my underlying flow is non-chaotic, is that enough to kill? So there is a coincidence. The lower dimension, I'm happy to stick my neck out a little bit more that it's not a coincidence. The higher dimension is something that, But the interesting thing, and I think it's worth looking at, is in stochastic models to understand the regularity of the flow and how that, because as you know, d equal to 3 is very special, because in dimension 3, you can show that you need the least regularity of a flow to sustain dynamo. So three-dimensional world is special.
Thank you.
Go ahead.
Yeah. So if I understood right, your magnetic fields are just vectors, right? You're just treating them as vectors in higher dimensions.
And dimensionalize in a suitable way to write the equations, yes.
Yeah. So now, if you just start with Maxwell equations in arbitrary dimensions, there would be some two forms and you'll have like some d choose 2 number of these things. So if you actually do that, would these results change? If you work with actual magnetic fields in d dimensions?
Good question. I actually don't know, because we were totally biased with the effect of the fluid. But that's a good question. Maybe it's worth looking at for some of them. Yes, that's a good question. Just in the Maxwell's equation, can you sustain? Yes.
Okay, let's thank Professor Samriddhi.